Hello, hello. My name is Mandeep, and I'm a KIPAC outreach coordinator, and I'm co-organizer with Dan Wilkins for this series. He announced the last one. So I'm going to speak up a little bit louder. If you can't hear me, tap your ear, as somebody just did. So before I announce today's lecture, I'm going to say that we have a couple that are coming up. They're usually going to be on the second Tuesday of each month, so watch your emails for them in case there's a date change. So next one is going to be on the third Tuesday just because of the speaker, and that's going to be Dan Holtz. That's going to be on gravitational waves, a different aspect than Roger Blanford, our inaugural speaker, talked about last time. So Dan has worked on a lot of LIGO. He's directly on the LIGO collaboration. And then we're going to have Wendy Friedman in February. Excuse me. And she's been one of the important people who've done a lot of measurement of the Hubble constant. So keep watching your email. Tell your friends. We're very excited about this, and we're going to be integrating with SLAC lectures as we go. This is the KIPAC lecture, and the SLAC public lectures are separate but integrating series. So today we're having Aaron Roodman, who has started as a particle physicist. So he's known as one of those who moved from the particle physics world into this world. And he did his undergrad at Caltech and his PhD at Chicago on CDF. So he was really working on the matter-antimatter asymmetry issues. And then he came to SLAC, I think, in 1998. And he decided at some point to stop thinking just about the half of the universe of half the quote antimatter that wasn't there. So I was about to say half the matter. So the antimatter that wasn't there, and started thinking about the 80% of the stuff that we can't see, the dark matter. And that's what he continues now. He's been really integral on dark energy survey, which is our currently running survey on a telescope down in Chile. And he's really he's heading the clean room where the camera is being built for the LSST, which he'll be talking about today. So without further ado, thank you, Aaron.
So in the 1920s, Edwin Hubble discovered that the universe was expanding. This is Hubble at the Hooker 100-inch telescope in the hills above Los Angeles. It took Alexander Friedman to understand why that expansion was occurring and to put it into context. Friedman used Einstein's new equations explaining gravity, general relativity, and found that the density of the universe would determine how the universe expanded and actually what the fate of the universe was. And from his equations, there were three possibilities. Possibility one, if the density of matter in the universe was too low, lower than some special amount, the universe would expand, and we would see distant galaxies, well, we would, if we lived billions of years, see distant galaxies receding from us into the infinite future. On the other hand, if the density of matter in the universe was too high, we would, again, if we could keep looking for billions of years, we would see the galaxies recede to us until some point they would stop receding and they would start coming towards us. Until, ultimately, all of the matter in the universe collected again into a big crunch, mirroring the Big Bang that began the universe. And the third possibility, if the density of matter in the universe was just right, the Goldilocks solution, then the galaxies in the universe would continue to expand away from us, again into the infinite future, but coasting. They wouldn't expand quite as fast as in the case when the matter in the universe was too low. So for 70-some years, cosmologists thought those were the three possibilities for the fate of the universe. The irony is that none of those were correct. And in fact, in the late 90s, two different teams, using observations of supernova, exploding stars and distant galaxies, determined that actually the expansion of the universe was accelerating. So it's not slowing down, not contracting, but instead expanding at a faster and faster rate over time. Now this was a remarkable discovery. In fact, the leaders of those teams won the Nobel Prize for it. And combined with measurements of the glow from the Big Bang, the so-called cosmic microwave background, so the glow from the Big Bang, we've been able to determine that actually the amount of matter and energy in the universe is the Goldilocks solution. It is just right. But the universe isn't continuing to expand, and it isn't expanding slower and slower. It's accelerating because the universe isn't made of regular matter or regular energy. A very large part of the universe is made up of something different. Now, we call that something different dark energy, but its unusual features are what causes the universe's expansion to accelerate. What we know today is that if we take all the matter and energy in the universe, 5% of it is ordinary matter, atoms. So Mandeep mentioned that I started my career in particle physics, and we thought we were learning about the fundamental building blocks of everything in the universe. But it turns out we were studying the fundamental building blocks of 5% of the universe instead. Around 27% of the stuff in the universe is a different kind of matter, dark matter, and the remaining, roughly 70%, is this other stuff, dark energy. Now, I have to mention one thing. We call it dark energy, but it's not exactly an energy. I mean, we can think of it like an energy, but you shouldn't think of it as an ordinary energy, an ordinary conventional energy. It's something different. Also, both dark matter and dark energy have the word dark in them. Don't be confused by that either. They're not the same. And as far as we know, they're actually not related. Now, what do we know about these mysterious components of the universe? What do we know about dark matter? Okay, we know its density. Averaged over the whole universe, it has a density that's equivalent to a little over 1 proton per cubic meter. So it's very dilute in the whole universe. It's not regular atoms. It's not made of the constituents of atoms, quarks or leptons. It does feel the force of gravity, but it doesn't shine, and it barely interacts with anything, including regular matter, including itself. That's really what we know. What about dark energy? Well, we know its energy density. So how much stuff of that is there per unit volume in the universe? Its energy density is equal to about 3 protons per cubic meter. Also, very dilute stuff. It's not regular matter, it's not dark matter, and it's not regular energy. It has the following bizarre feature. As the universe expands, the energy density of dark energy stays constant. Okay, so I'll pause. That's quite strange, right? If you have matter, regular matter, dark matter, doesn't matter which, you have a certain amount in some volume, and as the universe expands, there's more space, but there's the same amount of stuff. So the density goes down. Dark energy doesn't work that way. When the universe expands, the density stays constant. So that's strange. It also has another strange feature, which is really equivalent to the fact that its energy density is constant, and that is that it has negative pressure. So that's very strange, and there's no kind of good analogy to make there. Right? If you have a balloon filled with gas, the balloon is putting pressure on the gas is putting pressure on the balloon, keeping it inflated. If it had negative pressure, that'd be like the gas sucking in the balloon and contracting it. So basically, no regular matter, no regular energy acts that way. So it's strange stuff. Now, what can we measure about dark energy? So you'll see that the new telescope I'm going to tell you about, the Large Synoptic Survey Telescope, one of our main goals is to learn more about dark energy. What can we learn? Well, we can learn how much dark energy is in the universe. We actually already know that. We can learn about the pressure. We can measure that pressure. And we can also measure that pressure today, and we can measure it in the distant past. And by measuring it today and in the distant past, that is one of the ways we'll learn more about dark energy. Now, I mentioned that the density of matter and energy in the universe determines the fate of the universe. So I showed you a little graphic to illustrate the just right, the Goldilocks solution, or the big crunch. The accelerated universe looks like this. So this might be a distance between distant galaxies. This is time in billions of years. Here's today. So into the future, the universe is expanding. But the density, the pressure rather, which we always call W for the ratio of pressure to energy density, if that were -1, we'll expand like this. But suppose that ratio were a little bit more negative than -1. Then what happens? Then the universe expands even more rapidly to a point at which people have hypothesized that the universe would ultimately expand so fast that it would rip space-time apart. I'm not sure what that means exactly, I have to tell you. But it doesn't sound good. And some people think that actually it sounds so bad that maybe it really shouldn't be allowed. But this is something we can measure, this ratio. And it would be very interesting to know very accurately what that value is. And even more interesting to know whether it changes over billions of years into the past. That's all we can measure. So we're going to try to do that. Now, maybe I'll say one other thing about dark energy. There are different ideas about what it could be. One is that it's Einstein's cosmological constant. Einstein put in a constant term in his equations for gravity, general relativity, and he put that in because he thought the universe was static, that it wasn't expanding. And as soon as he learned the universe was expanding, he pulled that term out, but it's back. And that extra term would explain the phenomenon we call dark energy, in some sense. It would describe it. It could be a quantum field. It could be something like the Higgs field we know from particle physics that pervades the entire universe. Or it could be a modification of the laws of gravity, general relativity. But in any of those cases, there's one really weird thing. And that is if you do a very simple-minded calculation of the energy density that you might expect, you get a value that is 10 to the 120 times larger than what we observe. Now, that might tell you that the calculation is wrong, but it's a very simple calculation. So it has to be wrong in an interesting way. And a lot of people think that it's wrong in that way because it tells us something new and different about the universe. So that's what we're after. Okay, but how can we learn more about dark energy? What are we going to do? One way that we can learn more about it is to study how matter is distributed in the universe. And the distribution of matter in the universe will be different depending on how the universe expands. But we have a problem. Most of the matter is dark. It's dark matter. We can't see it. All we can do is infer its existence because it has the force of gravity. So we have to work harder. We can't do simple observations. So let me describe a little how we'll use our observations to study the dark part of the universe. So let's look at this simulation of the universe. This is a simulation, a computer simulation made by one of my colleagues here at Stanford, Risa Wessler, and her colleagues. And it shows dark matter in the universe. And it shows the collections of dark matter over billions of years as the universe expands. But it shows it in such a way you don't see the expansion. You just see the interaction of matter. And what you can see, the universe starts off much more uniform. But over time, the effect of gravity pulls lumps of dark matter together. And in this case, this collection here would be the center of a cluster of galaxies. It would be the center of, let's go back. Maybe we'll watch it again. So that region in the center would be where a cluster of galaxies would form. A cluster of galaxies might have up to 1,000 galaxies. So it's a region of the universe that's denser than any other sort of typical place in the universe. And so this shows how that might form. Now, seeing this structure is difficult, but there are different ways that we can do it. One of those ways that we can observe the dark matter is by seeing its gravitational impact. We can see that more distant galaxies have their light bent by dark matter. So if we have some very distant galaxy and we have lumps of dark matter between us and the distant galaxy, the light from those distant galaxies will be bent. And this is an image from the Hubble Space Telescope that shows that. This is actually a cluster of galaxies. So each one of these is a galaxy. These are all galaxies as well. But you notice there's something very strange going on. There are these arcs, these giant arcs, which are actually more distant galaxies whose light has been bent by the cluster of galaxies, and especially by the dark matter in that cluster, causing these arcs. Now, this is the extreme case, but it turns out that every single galaxy we see in the distant universe has had its light bent a little bit by the intervening matter. And we can observe that by looking at many, many galaxies. We can observe that effect. And we can use it to learn about the distribution of matter between us and the distant galaxies. Here's an example of that. And this is from a collaboration that I'm part of now called the Dark Energy Survey. And this is a map that we published this past year. And so the color scale is meant to indicate how much matter there is in that direction in the sky. So this is a map. You can see it's not longitude and latitude, it's RA and declination, so coordinates on the sky. But the colors here show whether you're looking at regions that are more massive or less massive than average. And by making maps like this, we can learn about the distribution of dark matter. And then by making maps like this, looking back at different times into the past, we can study how dark matter changes over time. And from that, we can learn how the universe has expanded, and then we can learn about dark energy. So it's a very complicated inference that we're going to do. So what we want to do is image as many galaxies as possible over as much of the universe as possible. We want to, in every one of those galaxies, measure the effect of gravitational lensing. By doing that, we'll map the dark matter in the universe. And then from that, we can infer the history of the expansion of the universe. And that will tell us about dark energy. So I'm sorry to say that it's actually not a simple process. But we have to go through this line of reasoning to see something that you can't see with your eyes in any other way. Okay, so with that, I'm going to change gears. And now I want to tell you about the telescope project that we're working on here at SLAC and here at KIPAC, one of whose goals is to do the kind of measurements I just described. So the project is called the Large Synoptic Survey Telescope. One thing I have to do is tell you what the word synoptic means, since it's not, I have to say I didn't know what it meant either the first time I heard the title of the project. So one definition is that it furnishes a general view over a large area at a point in time. That actually is a decent description of what we're doing, except that we're going to do it at many points in time. You'll see as I describe why that word fits. Okay, it's a new telescope, and it has a new instrument, a new giant camera that we're building now. It's been specially designed to try to do the kind of imaging that I just described we would need to study dark energy. It's made very specifically to see as many galaxies over as much of the universe as possible. And that's not the normal design for a telescope. It features an 8.5 meter diameter primary mirror. It has a secondary mirror that's almost 3.5 meters across. The field of view, so that's how much of the sky can you see at any one time, is 10 square degrees. The camera, and so the camera is of special interest here at SLAC because we're leading the camera project here. And we're building many of the pieces of the camera here at the laboratory, and we're assembling it here as well. The camera will be the world's largest digital camera, featuring a focal plane with 3.2 gigapixels. those pixels are spread over 189 CCDs. A CCD is a charge-coupled device. It's similar to the thing in your phone. But I have to say that the image sensor in your phone is tiny. It's really small. If you buy a $5,000 camera, sort of a professional grade camera, you'll get an image sensor that's the size of 35 millimeter film. So some of you might remember 35 millimeter films, so you know how big that is. Our CCDs are 4 centimeters square. That's much bigger. And we have 189 of them. The lens that we use as the first lens of the camera is 1.6 meters across, so about this high. And we'll collect each image in just 2 seconds. So that's all of that is a challenge, and I'll say a little bit more, I'll show a little bit more about how that looks. Now, I've been working on this project for about 7 years. Some of my colleagues, including Steve Kahn, who's a colleague here at Stanford, is the head of the project now. Some of my colleagues have been working on the project for 15 years. Over that whole time, we have typically shown engineering drawings like this one. So this is, you can tell it's a drawing of what the facility and the dome will look like in a mountaintop in the Chilean Andes. But it's very gratifying in the last year that instead of showing these sort of drawings, I can show this. So this is the observatory in August, and you can see it well under construction. The telescope goes inside here, so this is the dome. This swivels and rotates and opens so that we can look at the sky. And this is sort of the support building where we'll assemble some of the components, where we'll be able to, we'll sit and take the data, we'll have our computers there, our support equipment there. And actually, here's a picture taken in the last week. So you can see the building the exterior is basically done except for the dome. And then this is actually a little auxiliary telescope, which we'll use to monitor the atmosphere, which is an important thing for us to do. So this is fantastic to see. And so now the telescope is really in the heart of its construction. So let me take a little while and just show you some of the pictures from the construction and describe how the instrument works. So the heart of any telescope is the mirror. So this is the LSST primary mirror after the glass was formed, but before the polishing began. And let's go back. Okay, so this is probably 6 or 7 years ago. And actually, the primary mirror has been completed. So here it is after polishing. And I like this picture because you can see very clearly that it is really 2 mirrors in one. The outer section is the primary mirror, and the inner section, the inner portion, which has a different radius of curvature, is actually the third mirror. So we have a 3-mirror design. And to explain that more fully would take a bit of an exposition about optics. But because we want to look at such a big field of view, we want to take images of so much of the sky at once, having a third mirror is a big aid to that. And it allows us to have very high-quality images over this very large field of view. So the mirror has been completed. It's actually sitting in, well, at least as of a few months ago, it was sitting in a warehouse in the Tucson airport. There's actually a little more work they're going to do on it before it's shipped to Chile. Here's the secondary mirror. I believe this is the largest mirror of this kind ever built, at 3.5 meters across. So that's the piece of glass. And here's what it looks like after it's been polished and is actually on a testing jig. And so that mirror is also basically done. The next important piece is the telescope mount. So this is a picture taken in the last week at a factory in Spain that shows you the structure of the telescope. So here's a person to give you the scale. So it is large. The mirror will go kind of in the back here. This is the axis which the telescope sort of tips up to look at different azimuths. And then the whole thing will rotate around. I mean, different elevations, rather. And then the whole thing rotates around to different azimuth. The camera, which I'm going to talk about in a second, fits in here. So where this yellow piece of metal is where our camera will fit. It's fantastic to see this thing taking shape. Now, One other interesting thing that I can point out, you'll notice, well, if some of you have seen pictures of other telescopes, or if you have a little telescope in your backyard, you'll know that they're usually a little bit longer. This one is extremely squat. And it's squat for two reasons. First, it's squat because the F number is very low. So if you know about camera lenses, you know that a low F number is a fast camera lens. And it means you can get a picture that has only a little bit in focus, with sort of things behind you out of focus. And it also collects a lot of light. Those are all features that actually we want. And so we have a very low F number. Our F number is 1.2, which is really lower than any other kind of comparable telescope. The other reason it's good to be squat is that we want to take images of the whole sky, and we want to do that rapidly. And so it turns out we want to move the telescope quickly from pointing in one direction to another direction. And to do that with a long telescope is actually difficult, or to do it fast with a longer telescope is harder. It's a little easier with a squatter telescope. So that drove the design to be what this looks like. All right, let's move now to the camera. So the LSST camera, I said it's going to be the largest digital camera ever built. So here's a drawing of it. Now, unfortunately, I cannot show you the full camera, okay, because the camera today is in pieces, being constructed here at SLAC, at one of our partner labs on Long Island, Brookhaven Lab, some companies in Tucson, some companies in France, some collaborators in France, and a few other places. So we only have these sort of engineering drawings to look at. The camera consists of 3 lenses. You can kind of see them cut out. 1, 2, and then the third one is here. This lens, as I said, is 1.6 meters across, so like this. I think it might, I know it's the biggest lens ever built for astronomy. No one will say whether it's the biggest lens ever built, because I have a feeling, well, I don't have a clearance, so I can say this. The people who build these lenses do work for the military, and so they won't say it's the biggest lens they ever built, but I have a feeling it's because they've built bigger lenses that are in space looking down. But they won't confirm that for me. It has, so the focal plane is here, that's kind of the hatching. There's a very large cryostat, so that's a vessel to keep the image sensors cold. To operate these kinds of image sensors, you want to cool them, and in our case, that's to a temperature of minus 100 C. To do that, they have to be in vacuum, and then you need a special refrigerator to keep them so cold. That is all back here, and the refrigerator is mounted in the back with electronics and vacuum pumps and other support equipment. The other thing we have is a filter. That's the red filter is shown here. And we use a filter because when we take images, we don't want to take them over the full wavelength of light that our sensors can see. We want to look at a more restricted band of wavelengths. And we actually have 6 different filters. And that enables us to study features of the stars we'll see and to study the galaxies more closely. And in particular, it lets us measure the galaxy's redshift, which is proportional to how the galaxy is receding away from us. And it's all packed together into this actually very small package. So almost every inch of space is used in here. And it's going to be a major challenge just to assemble it. Here's an exploded view. Maybe I'll skip that. Here are some of the components under construction. So here's the first lens being polished. Here's the second lens. So you can get some idea of the scale from the people looking at it. The second lens the polishing has been completed, and the next step is actually to have it coated. The lenses have a special coating, an anti-reflective coating. So if you pay a little more, you can have your eyeglasses coated with something to prevent glare. We have something very similar here, because we also don't want to lose light reflecting off the surface. This object is interesting. This is what we call the grid. It's actually the component that will hold up the structures that hold the CCDs. And the interesting thing about it, it was constructed such that these features, which are the mounting features, are flat to 4 microns. So a micron is a millionth of a meter. So a piece of paper is 150 or 100 microns thick. And so this is flat to 4 microns. And we want it to be so flat because of the optical system that we're using. So I mentioned this F number, that the system was a very fast system. And what that means is that only that the position that's in focus is very narrow. And so you want to have your image sensors in a very narrow spot to keep them in focus. And if they deviate, if some of the sensors are above that spot or below that spot, then those sensors will be out of focus, which of course we don't want. So we have to build it actually to very tight tolerances. And that kind of tolerance we keep in many pieces of the camera design so that we can stay in focus. And then the last thing to show here is the filters. And so this is at a laboratory in France. This is a prototype of the filter exchanger. And it turns out that that is tricky too. And you can kind of see it here because the filters are large. The filters are about this big. And it turns out there's no good place to store them. So they're actually stored kind of on the side. Well, not this far on the side, but kind of on the side of where the focal plane is. And to pull them out of that spot and put them into place, we have this device, this filter changer, which is kind of a mechanical thing that grabs this filter. These filters are, I don't know, $500,000 objects maybe, several $100,000 objects. I forget what the cost is. They're expensive. We're only making one of each kind. So it's a delicate operation. But this filter changer kind of grabs them, pulls them into place, and then when it wants to change them, there's this carousel that rotates around. So it's a very tricky design. So this is the carousel that rotates around. It's a tricky design, but really highly optimized so that the camera fits inside this cylinder. So even though it's a giant telescope and a very large camera, we're actually pressed for space. Now, I mentioned that we're building the camera here at SLAC. So I thought it'd be good to show you a few pictures of my colleagues working in the laboratory. And so this is our laboratory in one of the buildings on site. It's a giant clean room where we're going to do all the camera assembly. So for instance, here are a couple of my colleagues looking at one of the sub-assemblies of the camera. So what they're looking at is a piece, we call it the raft. That's just our name for it. And it has 9 CCDs. I think you can just barely see the hatching between the 9 CCDs. So each CCD is 4 centimeters square. So this is 12 centimeters square. This alone is a 144 megapixel camera. So by itself, it's one of the largest cameras ever built. And we'll have 21 of these put together. So this is one of the prototype ones, and they've just put it into this dewar and are about to start working on testing it. I think this might be me, but this is one of my colleagues looking at some of our apparatus to test a single one of these rafts. And so we have equipment that lets us shine different patterns of light on the CCDs, and we can do studies to make sure that it's working the way it should. And here's the raft kind of out of the dewar. This is another interesting feature of our camera. This is the readout electronics. So this is the electronics that will digitize each one of those 3.2 gigapixels and have them read out, so turned into a digital picture in 2 seconds. And that electronics was built here at SLAC as well. And lastly, here's some other of my colleagues working to take one of these devices, which was just shipped to us from Brookhaven Lab in Long Island, and take apart its complicated packaging to get it. And this was just a couple weeks ago. So the camera is underway. Almost every piece of it is being built. We haven't really put anything together yet. But that's going to happen over the next 2 years. And in fact, we're scheduled to deliver the camera to Chile in the spring of 2020. So we feel like the clock is ticking. So that's the apparatus. And now I want to change tacks slightly again and tell you about how we're going to observe the sky. because that's the other unique thing about LSST. For many other telescopes, the telescope is used in sort of a different way every time someone uses it. People might point at one object, another object. People might look at a restricted region of the sky. LSST is different. We have a survey planned. So we are aiming to look at the entire southern hemisphere sky, and we're going to look at it every night for 10 years. And we'll do it in a particular pattern to optimize the kind of science that we can do with these images. Now, the mantra of the project is that it's going to be wide, so it will look at a large swath of the sky. And so this plot is meant to show the density of images on the sky. There are actually a few regions that we'll look at even more often. And then this region is where this is the galaxy. And so you can't look at the galaxy, you can't keep looking at it with any profit because there are too many stars. And so once you've seen the stars, you can't really do much more. But we're going to look at the entire sky. We also say it's fast. So in that every image, we'll look at a big swath of the sky. I mentioned that it was 10 square degrees. So about 3.5 degrees across. By comparison, the moon is half a degree across. So that shows you the size of each picture on the sky. And then it's fast in the other way that I mentioned when I described why we had a squat telescope, that will look at the sky quickly. And so this is a simulation done of what the observing pattern might be. So this is over the course of a night, so it's night 364, and you can see each one of these little circles is the focal plane. Oh, now it's the next night, night 365. And you can see it's tiling the sky. Sometimes we'll take images kind of nearby, and then occasionally we'll jump to some other region of the sky, depending on what's important to fill in that night. And we'll do this every night for 10 years. There'll be a few nights off, perhaps, for fixing equipment, but this gives you an idea of the kind of observations we'll make. Every observation will be 30 seconds long. We'll take two 15-second images back to back. And of course, that's so fast, there's no way that a person could do it. So the decision about where to point the telescope will be made by computer. And last, we say that the survey is going to be deep. That's astronomy jargon. That means we're going to look at the dimmest objects, the most distant objects, or medium, or objects that aren't quite as far away but are extremely dim. This is a simulated image, so this is not a real image, but it's meant to be representative of the kind of images that we'll get with LSST. So given the speed of the telescope and the speed of the camera, we think we can see every part of the available sky in 3 or 4 nights. That corresponds to about 15 terabytes of data every night. Today, maybe 15 terabytes a night doesn't seem like so much. I can tell you when I first heard about this project about 15 years ago, that number seemed terrifying. Today it's not as big. But you'll see in a second, actually, some of the computational challenges are extreme. So we'll take images every night, and at the end of 10 years, our data sample will be something like 50 or 100 petabytes. Every spot of the sky we should see about 1,000 times. Now, with that data, we estimate we will observe 20 billion galaxies. That's a significant fraction of the total number of galaxies in the visible universe. We think we'll see 17 billion stars in the Milky Way. The estimate is we'll see 6 million objects in the solar system. Everything from, well, if Planet 9 exists, I think we have a very good chance of seeing it. And we'll see 90% of all the killer asteroids, we estimate, and everything in between. Every night we will get maybe up to 10 million, somewhere between 1 and 10 million alerts. I'll tell you in a little bit what an alert is. And the database, we think, will have 50 trillion objects. So an object is an observation of a star or a galaxy or an asteroid. Now, actually, that's the piece that's really computationally difficult, because we will have a database with 50 trillion rows. And that doesn't exist anywhere. And we will want to access that giant database in some reasonable way. We might also need a system where multiple scientists in the US could access that database in a reasonable way. That's a major challenge. And so even though the raw data volume, at 50 or 100 petabytes doesn't seem like so much today, this is a problem. This is a really large number. Okay, now, in addition to studying galaxies and studying gravitational lensing of the light from those galaxies and studying dark energy, we're going to do a lot of other science. And one of the most interesting facets of that, of the range of science that we can do are connected to the alerts, are connected to things that change in the sky. Because we're observing the same part of the sky so many times, we're ideally suited to look for anything that changes. And so we'll have a system that will automatically flag any of those changes. The way it works is, well, there's some complication, but basically we'll have a repository of images of the sky, and every time we take a new image, we'll compare it to the reference image. And if any object has changed in position, or has changed in its brightness, or gotten brighter or dimmer, or whether a new object appears, that will be flagged. And we call that an alert. We expect between 1 and 10 million of those every night. In addition, they'll be detected within about a minute of the observations being taken. So there'll be the computational facilities to do this calculation in real time. With that system, we'll see new objects in the sky, supernova. We'll see changing objects, variable stars or nova. We'll see moving objects, those are in the solar system, and new or unexpected phenomena. The other interesting thing is those alerts are, well, we call them public. So they're available to the entire US scientific community, and in some restricted form will be available to the public as well. And actually, one of the big questions people have is, how can people keep up? How are people going to be able to monitor that stream of alerts and pull out the kind of objects that they're interested in? That's actually an open question in the project that individual scientists have to figure out for themselves. Now, what are some of those interesting transients? Well, there was one that occurred this past fall, you might have heard about. So there was the gravitational wave detectors, LIGO, in the US, and Virgo in Italy. Well, LIGO especially saw a gravitational wave event. They've seen a couple so far. But in this one, when telescopes got a signal from them that they had seen a gravitational wave event, people pointed their telescope in the general direction. This one was good because the general direction was relatively contained. And this is from the other camera project I've been working on, DECAM. This is an image of a nearby galaxy. And what was observed by my colleagues on DECAM and several other telescopes as well was this object. And then 2 weeks later, it was gone. And this was the bright spot from a neutron star collision. Now, one of the reasons DECAM was so good a device to look for a transient, so an interesting new object like this one, is because DECAM also has a wide field of view. LSST's is even bigger, is 3 times larger. And this object, we kind of got lucky because it was so nearby that the transient, so it's being called a kilonova, was quite bright. But I can imagine as we see other gravitational wave events that some of them will be much dimmer. And in that case, you want to have a big telescope to look for them. It would also be very interesting if you're able to point to the interesting direction as soon as possible after the gravitational wave event occurs. We may be able to do that with LSST as well. So this is a harbinger, I think, of some of the interesting new kinds of science that we'll do with our survey. What else can we do? So one, I mentioned that we can look for objects in the solar system. Here's an example. This is also from the Dark Energy Survey from my colleague at Michigan, Dave Gerdes. And so this is repeated observations over a couple of years, let's go back, of let's start it again, of a couple objects in the Kuiper belt. So that's at the edge of the solar system. And you can see those objects. Since they're nearby, they appear to move with the Earth's rotation around the sun. So we'll look for planet 9 in roughly a similar way. We'll look for lots of solar system objects this way. And then for objects that are even closer, for asteroids, we have to look at them in a different way because they move so fast. But combined, we expect that we'll see a huge number of objects in the solar system. So this is a much different kind of science than studying dark energy. But the people who are interested in the objects in the solar system are very excited about LSST. Because to date, while individual objects have been seen, if you compare the number of asteroids that have been observed compared to the estimates for how many are out there, we've only seen a tiny fraction of them. But LSST, we think we'll see not all of them, but almost all of them. And in fact, sometimes I think that the first interesting pieces of science to come from LSST will be this. But what I fear is that as we discover asteroids, we'll find that some of them look like they're on orbits that might be Earth-crossing, so the killer asteroids. And so the first thing that will come out of LSST are messages of doom that there may be asteroids headed for the Earth, in 10, 15, 100 years, only for us to discover as they're better measured, no, that asteroid will not hit the Earth after all. So that might be what happens first from LSST. I think studying dark energy will take longer. Okay, so here's just a picture of an asteroid from some other telescope, just to show you that actually asteroids are moving so fast, sometimes you can even see them move in a single image. So I want to close actually with one other mention, and I alluded to it, that some of the data from LSST will be made available to the public. Not all of it. We'll have too much data, so I think not all of it will be. But some subsets of it will be in forms that are really appropriate for the general public or for the interested citizen scientist. There exists already a number of interesting projects that you can find on the web that use astronomical data and let people use their eyes to aid astronomers in discoveries that are difficult to make by computer. One of them is called Galaxy Zoo, which was a project to look at images of galaxies from a different survey from about a dozen years ago called the Sloan Digital Sky Survey. Yet another is called Space Warps to look for the kind of gravitational lens arcs that I showed a picture of, some of which are very hard to detect via computer. And in both cases, images from the telescope and camera are made available, and there's some training information on the websites. And people are encouraged to look at those images and just describe what they saw and to try to find phenomena. And actually, in both cases, individual people found interesting things. I hope that we'll do something similar with LSST, but in our case, the amount of the data and the sort of the data will be of a totally different character. So with that, I want to just give you some final thoughts. So I mentioned that we're a couple years away from delivering the camera. Actually, I've given similar talks over the last couple of years, and so 2020 always seemed like a long time from now. Now it doesn't, since we're almost at 2018. And some of us are, feverishly working and excited about the next 2 years. For the observatory as a whole, we expect first light, so the first time you take an image with the telescope, to occur also in 2020. And we have about a year and a half or so of time to get everything working perfectly, and we hope to start the survey, the 10-year survey, in 2022. And the one last thing I want to mention is that LSST is almost entirely funded by federal dollars. The camera is funded by the Department of Energy's Office of High Energy Physics that funds, the Department of Energy funds SLAC. And the telescope and all the computing are funded by the National Science Foundation. So you are paying for our project, and I can tell you that we thank you for your support. And I'll close there.
So we have some time for questions, so go ahead and raise your hands. And the mics are actually on the table, and so when I call on you, just press the button on your mic, and we'll go. So go ahead.
I'll repeat it. I'll repeat the question.
Thank you for a very exciting talk. A question is, how are you going to move all the data from the summit of a mountain to your data center? And I understand, I believe, in real time or close to real time.
So the real-time analysis will be done at the base camp in the town of La Serena. So it's a medium-sized city on the coast in Chile, about an hour-and-a-half drive from the observatory. So yeah, some of the real-time work can be done there, but actually the data will be transmitted just over the internet. We have some special high-speed lines that we'll be using, and actually, even though it's a huge amount of data, it will not be a problem to just ship it over fiber. It actually goes to the supercomputer center at the University of Illinois, so all the processing will be done there. There'll be a satellite data center in France. The data that people want to access, some of that may be in Tucson or it may be in Illinois. Actually, I don't remember. But yeah, just fiber. So just the way all the other internet traffic goes.
Yes, not working. Okay. During the talk, you referred to a multi-step process that's required to get to the determination of dark energy. Could you say more about how gravitational lensing fits into that, why that is required?
Yeah, okay. So let's go back. Let's see. Okay, so let's go back, let's look at this image. So I mentioned this is an image of a cluster of galaxies. So this is an extremely massive collection of galaxies, so massive that galaxies that are behind it, as we see it, have their light bent, like so. Now this is the extreme case. Every galaxy has its light bent a little bit, and we can measure that statistically. By looking at millions, or in our case, billions of galaxies, we can measure that effect on average. The other key feature is that the amount of stretching of the galaxy is proportional to the amount of matter nearby. And so that's the key link. So by measuring how much each galaxy is stretched, you can learn about how much matter is nearby, and then that tells you about the distribution of matter in the universe. The other thing that I didn't go into as deeply is so we'll measure how matter is distributed in the universe. Why does that tell us anything? There's actually the phenomenon, in description is simple. When the universe begins, there are different regions of the universe that have a little bit more matter than their neighbors. So if you've got a region with a little bit more matter than any of your neighbors, you have a bigger gravitational attraction. And so you'll attract nearby matter to you. Then that region of the universe has even more matter than its neighbors and will attract yet more matter to them. Now, as that process goes on, there's another process that acts sort of to counter that, and that's the expansion of the universe. If the universe expands faster, then the neighboring matter is further away and doesn't have a chance to collect at our dense region as much. If the universe expands more slowly, then there's more of a chance for the neighboring matter to collect. So by studying the distribution of matter and what I just described, you can learn about how the universe expanded. And you can also do that, you can look at the expansion today, but you can look at it 1 billion years ago, 2 billion years ago, 5 billion years ago. And it's the difference in the expansion over that time that maps out the full expansion history of the universe. And that's what tells you about dark energy.
Because we have some of that now, we'll have it much more precisely with this data.
Right. What I've described has been done by a couple different telescope surveys, one of which is the one I've been working on myself, Dark Energy Survey. There's one in Europe that's done something similar. And then there are a couple of older projects that have also done that. There's a telescope, it's a Japanese telescope in Hawaii that has a very nice camera that will do something similar. We'll be able to do it over a very large region of the sky with many more galaxies, so we should be able to do it better. Okay, let's see, with the microphone.
You mentioned the Universal camera is f1.2, so that the region of focus is very narrow where there's very low depth of field. Yet you're looking for objects of varying distances away from the telescope. Are you going to focus it? Are you actually going to shift around?
So it turns out in astronomy, everything is so far away that it's in kind of the infinite distance limit. So you don't need to focus for objects. Okay, so everything we see is in focus because it's so distant. The one exception is if you see an airplane go by. And then the trail, there's one good image from the Dark Energy Survey where an airplane went by just as we were taking our exposure, and you can see the lights blinking from the airplane, and those are out of focus. But everything in the heavens is in focus.
Okay. Actually, the buttons do work now, I'm pretty sure. So let's try that one there. Press the button. See if it works.
That works. In the beginning of the talk, you said that the energy density, dark energy density is constant, even with the universe expanding. Does that mean as the universe expands, it's creating more dark energy?
It kind of does, yes. And if it sounds to you like that violates the conservation of energy, well, you should know that in general relativity, energy is only defined locally. So you can have such things happen and it doesn't really violate the local conservation of energy, but it does seem strange. But yeah, that's how it is.
So I know you described some of the properties of dark energy, right? Like negative pressure and so on. But what do we expect out of this? Like, what do we think it is? What's the best case? And I know it's a big unknown, right? But what are some of the best cases?
So the three things I mentioned are that's sort of the way you could summarize the different ideas. So the top one, the cosmological constant, that is definitely people's favorite view. Some of my colleagues are convinced that's correct. And it is true that all of the data that we have to date is consistent with that. The other two possibilities are actually more and more constrained. But our measurements are still, we can improve our measurements an enormous amount with the kind of data we'll get at LSST, and actually I should say from some other cosmology projects as well. So both of these are possible. And actually, maybe I'll say a bit more about the quantum field. So dark energy, if it were a quantum field, has certain properties that are very, very similar to the Higgs field. So if I should not assume that people know what the Higgs field is. So the Higgs field is the thing that gives the electron mass in the theories of particle physics. The Higgs field produces, or part of the Higgs field phenomenon is the Higgs boson. And the Higgs boson was discovered at the Accelerator Lab in Europe, CERN, maybe it's 5 years ago now. A couple of people won the Nobel Prize for that. The Higgs field and dark energy, if it were a field, actually have very, very similar structure. Now, there's a third quantum field that we think exists that would pervade the whole universe, and that is the thing that causes inflation. So this is not sometimes physicists use words that are used in common lingo. Obviously, inflation here is not the fact that things are going to cost more tomorrow. Inflation, if you haven't heard about it, is the idea that in the very, very first instant of the universe, the whole universe expanded in an accelerating way a spectacular amount. Then, after this first instant, that stopped and the universe expanded kind of in the normal way that I described. Now, the evidence for inflation is not conclusive, but some of the observations we have are very consistent with this period of inflation in the first instant. Instant here means like 10 to the minus 35 or 10 to the minus 33 seconds. So really an instant. Now, that period of the universe, the expansion of the universe then had to be due to something very similar to dark energy, except that the density was much higher then than the dark energy today. So the quantum field, I think, is an interesting possibility because there are two other things we observe that kind of smell the same. But that's not evidence, that's just suggestive. Modification of general relativity, I can tell you most people don't like that because general relativity is so beautiful, why should it be modified? But it is possible, and some of the measurements we'll make will be designed not to study dark energy, but to study general relativity. And it's possible we could see evidence for deviation, for general relativity not being right. But these are kind of the best three possibilities.
What happens to the camera after your 10 years is up? Do they retire? And
God, I just want to have it built, working on the telescope. Yeah, what happens in 2032, I'm not sure. So I actually don't know the answer to that. We have, so we've planned for this 10-year survey. It is possible after 10 years that, I think it's likely that the instrument and the telescope would be used in a slightly different way. I suspect that the camera could be used in a different way than just continuing the survey. I think it's unlikely that we would just continue taking data in the same way we've taken it the first 10 years. I think that's unlikely to be interesting by itself, but it's possible we could make some improvements to the camera, we could make improvements to the telescope, and we could continue to take images of a somewhat different flavor. But actually, I don't know. Some of us have devoted a little bit of time thinking about that, and it's true that these sort of big science projects take so long that these days you have to think about not about the next project before the current project's even started, which is today. So we are thinking about it a little.
So are you working with any other experiments to combine data and collect to collaborate?
So the question is, are we working to combine data? Yeah, I think we will. So certainly the example of the gravitational wave detectors is one way. There are some other instruments. There's a neutrino detector in the South Pole that gives alerts when they see an interesting neutrino. That's something else one could look at. The other thing that we will probably do is that there are also plans for space telescopes. There's one in Europe, and there's going to be one in the US, also in the next decade. And both of those space telescopes have, as part of their scientific goal, studying dark energy. Their capabilities are different and in some ways complementary to ours. So I think it's likely that we'll share data among these different surveys to try to make the sum a bit more than to be the sum bigger than the parts. So, yes.
I think we're just going to go with one more. I think you had your hand up, and then we're going to ask people that don't.
Thank you again for a very interesting talk. Actually, I have two very short questions. In the history of astronomy, Halley's Comet played a major role. And when Gauss was able to predict its reappearance in the sky. Will you be able to image Halley's Comet? And the second question,
Don't
while
know.
you're
the
thinking
answer is
about
I
that.
don't know.
Don't know.
Actually, I
Okay.
doubt it,
The
but I
second
don't.
question, is there any thought of exploring whether some of the presumed constants of nature, like the speed of light, Newton's gravitational constant, Einstein's cosmological constant, whether they actually vary in time?
So yeah, so the first question, Halley's Comet, I don't know, but probably not, since I think it's so far away from the sun that it's too dim. And then variation of the fundamental constants. I've not heard of anyone think about using this data for that. People have studied that in different ways. So far, no one has seen anything suggestive of that. One thing I will say, because the data will be available to the whole US scientific community, actually some significant fractions of the scientific community in other countries, I have a feeling people will come up with lots of clever things to do with it. I don't know if it'll be that, but I'm sure it will be things that are unexpected.
So I think there's, I think we have Aaron's here, and Greg is here, and Roger is here. So they're going to stick around for a few minutes and answer questions one-on-one. But I think let's thank Aaron again for a great talk.